Swayam Prabha. Digital India. Educated India.
Hello and welcome to this lecture on control systems. In the last class, we looked at block diagram reduction in a closed loop control system. And then from there, we looked at the response of a spring mass damper system. And we said that the link of a robot is modeled as a spring mass damper system. And depending on the values of M, B, and K, it behaves in a particular way. For example, it could be overdamped, underdamped, or critically damped. Now from there we designed a very simple control system, a very simple controller called the position regulator. Now in the position regulator, the function is essentially to keep the block in a particular position irrespective of small disturbances. And today we'll move on to the study of a single joint, of a single robot joint. Now I had explained in the previous classes that every joint is connected to a motor. We give a voltage to the motor rotates, and the motor is connected to a gear, and then the gear rotates the link on the other side. Okay, so we look at this structure, derive and then propose a controller. First we'll start with a P controller, then PD controller, and then PID controller, and then look at how the system behaves and things like that. Okay, so let's proceed with the control of a single joint manipulator today. So we are looking at the control of a single joint. Now, as I said in the last few classes that the control structure is essentially independent joint control. So every joint is controlled similarly. Okay, so if you study the control of one joint, we can understand how the other joints are also going to be controlled. So how the robot actually works is at the joint we have a motor. Okay, so we have a motor which connects the joints. So we have a motor for actuation of the joints. The motor is connected to a bearing, and the bearing is connected to a gear. Okay, so there is a gear here, and the gear is again mounted on a bearing, and then there is a link on the other side. Okay. So basically we have a motor, then we have bearings here. Okay, bearings to support the shaft of the motor inside. Then we have gears. There is a gear ratio of N, and there are bearings on the other side also. Okay. Now let us write the various terms that we are going to examine. Now the motor produces the torque tau m, and there is a rotation angle is theta m. Okay, at the bearing there is friction which is Fm, and the inertia of the motor is Jm. Okay, on the motor side. Then there is a gear 1. This is my N1 is gear 1, and N2 is gear 2. Okay, which has a gear ratio of N. Then on the link side we have a bearing again, which has so there is theta L is the rotation angle here. There is a bearing which is Fl, which is the friction coefficient here. Okay, and then this is connected to a link. So this is my link, and at the link head it produces a torque which is tau L. So sorry, TL is the torque. Then this is my friction is already there, and we have the link inertia with this JL. Okay, so how does the actual joint actually work? Okay, so how this actually works is we give voltage to the motor will rotate. When the motor rotates, the gear rotates. The gear rotation will be transmitted from gear 1 to gear 2, and then it will rotate the link. Now why is the gear used? Because we know that the torque produced by a motor, DC motor, is not very large, so it has to be amplified in order to move the link. And the second is to reduce the speed, because the DC motor will have a very high speed, maybe about 2,000 or 3,000 RPM. So it has to be reduced to a much smaller speed, and that is why a reduction gearbox is used. Okay, so this is the basic setup for a DC motor with a gear reducer. Now this is the basic setup for actuation of a joint using a DC motor. Now let's start off looking at the analysis. So theta m by theta m is equal to N, which is the gear ratio. Okay, so this is my gear ratio. Then theta L is equal to N times theta m. It's a reducing gearbox, so it is going to reduce the speed of the motor. If I take the derivative of this, then theta L dot is equal to n into theta m dot. And further, if I take the derivative again, then theta L double dot is equal to n times theta m double dot. Okay, and this is my equation number 1. Now for gear 1, the equation of motion, now we are looking at this from the gear 1 side, okay, so from the motor side, then we look from the link side. Now from the gear side, for gear 1, the equation of motion for gear 1, the equation of motion is given by Jm theta m double dot plus Fm theta m dot plus T1 is equal to Tm. What is T1? T1 is the torque acting on gear 1, which is coming from gear 2. Okay, so T1 is the torque on torque on gear 1 from gear 2. So this is one equation. Let's call this my equation 2. Okay, so the torque produced at the motor by the rotation of the rotor overcomes the friction, and then it's used to overcome the torque on gear 1 that is coming from gear 2. So this is my total torque tau m. Now if I write for gear 2, so I was looking in this direction. Now if I come from this side, what do we get? We get the link rotation, okay, JL into theta L double dot plus friction is equal to the torque coming on joint on gear 2 from joint gear 1 plus the dynamics of the link. Okay, so that is what we are going to get from when we are looking from the link side. So for gear 2, the equation of motion is given by JL theta L double dot plus FL into theta L dot is equal to the the torque on gear 2 plus the torque due to the link. Okay, so T2 is torque from gear 1 on gear 2, from gear 1 to gear 2. Okay, and tau L is the link, is from the link. When the link is rotating, there is a disturbance torque. Okay, so this is my disturbance torque, which is also called dynamics, which is also the dynamic torque actually. Okay, so this is from my link. Let me call this equation 3. So we have looked at it from a gear 1 perspective and from the motor side, and then we are looking at it from the gear side, from the link side. Okay. Now, assuming conservation of energy, we have that Tm, the torque which is acting on gear 1, is equal to T2 into theta L. So this is for conservation of energy. Okay. Now, putting 1 in equation 3. Equation 1 was giving the relation between the link side velocity with that of the motor side velocity. So what we are doing is we are converting this equation 3, which is variable is theta L here. So I can convert it in terms of theta m. So what we do get is n times JL theta m double dot plus n into FL theta m dot minus TL is equal to T2. Okay, so we are using the relationship that T1 theta m by theta L is equal. Okay, so this becomes equal to T1 by n. Okay, so in equation 3 we have used the relationship that T1 by n and replaced, so which was equation 3? This is my equation 3, and so what we have done is T2 is torque from gear 1 to gear 2, and we have this relationship from conservation of energy. Okay, so what we have basically done is putting 1 in 3. So I didn't write that down. So putting 1 in 3, we get this equation. Okay, so we get this equation now. Now we have converted everything in terms of theta m. Now putting 5, let's call this equation 5. Putting 5, equation 5 in equation 2. Okay, which one was equation 2? We can have a look at equation 2. Equation 2 was the motor equation. So what I'm basically doing, I'm replacing, I'm putting this equation 5 in equation 2. Okay, so this is my equation 2, so I'm putting this here, and what do we get is Jm theta m double dot plus Fm theta m dot plus n squared Jl theta m double dot plus n squared Fl theta m minus n times tau L is equal to Tm. Okay, now what we can, so how did we get this? We basically made use of this conservation of energy equation. Okay, and then I took my equation 1, put it in equation 3, and from equation 3 I combined it with equation 2, and this is what I get. Putting 5 in 2, this is what we get. Okay, so what we see is that everything has been reduced to theta m only now in terms of velocity and accelerations. So what I do is I take theta m double dot comma theta m Jm plus n squared Jl into theta m double dot plus Fm plus n squared Fl. Okay, theta m dot is equal to Tm plus n times Tl. Okay, so this is my equation number, let's call this equation number 7. Now this is a very, very important equation, and it tells us why a linear control system actually works reasonably well for controlling a robot manipulator. Now that is because if you observe this equation very carefully, we find that this n squared comes here. There's an n squared here. So it basically means, and there is an n here. Okay, so it basically means that the disturbance torque is going to be reduced. Okay, and the effect on the load inertias is going to be reduced by n squared. Okay, so the observation which is very, very important here is n is small, less than or equal to 0.01. Okay, the effect of, and because of which the effect of load inertia and load friction is reduced by n squared. The effect of load inertia is reduced by, so this is a very, very important observation, and it also tells us why a linear control system works. Theoretically it should not be working, but it does work, essentially because of this gear ratio being there. That is one. And the second is that the effect of dynamics is reduced by n. That we can see here, okay, which is given here. So there is disturbance, yes, but the disturbance is reduced by a factor of n. Okay, and because of which linear control systems work for a nonlinear robot manipulator. So linear control systems work reasonably well for a robot manipulator, which is essentially nonlinear. Okay, so this is something very, very important that we need to understand. This equation is a very simple equation. How did we get it? I explained, but this very, very important equation because it tells us that a linear control system actually works and why it works. Now let us proceed further and look at the model. So we have modeled the mechanical, the rotor and the link side. Now let us model the servo motor that is working. So model of DC servo. Now the link is going to be controlled by a DC servo motor. Okay, so we need to model that also. Now if you look at the internal construction of a motor, then basically what we have, we give a voltage input, then there is a resistance, and there is a resistance and there is an inductance. So there's a resistance and there is an inductance, okay, in the rotor. Okay, so let me draw my resistance and let me draw my inductance. Now on the outer side there is the link which is going out, which is moving, and then this is my the winding, okay, inside the motor, the rotor. So the plus minus is the voltage in. So let's say VA is voltage in, which I'm giving to the motor. There is a resistance RA, there is an inductance LA, and there is a current in the armature which is IA. Okay, and there is a rotation of the motor which is theta m dot. Now because this is rotating in a magnetic field, there is going to be a back EMF. Okay, so there is a back EMF VB. Okay, so what is the various parameters here? R is resistance, L is inductance, V is the input voltage which I'm going to give to the motor, and VB is the back EMF which is being produced, and IA is armature current. Okay. Now in terms of the torque produced by a motor, tau m, so this is the torque tau m which is going to be produced by the motor here. So I can write down RA is resistance, okay, LA is inductance, then VA is voltage input, VB is back EMF, okay, and tau m is motor torque. So now we know the motor torque is equal to KT, motor constant, into IA, the armature current, okay, and VB, the back EMF, is equal to the back EMF constant kg into the motor velocity, tau m, okay, where KT is the torque constant, the motor torque constant, which is defined by KT is the motor torque constant. And kg is the back EMF constant. So kg is the back EMF constant. Okay. Now the dynamics of the circuit, if you're looking at this, this is written as, from Kirchhoff's law we can write LA into IA dot plus RA IA is equal to VA minus VB. So the total voltage in the system is VA, and the back EMF is opposing it, so it is minus VB, which is equal to VA minus kg into theta m dot. Okay. Now we know that for a DC motor, LA is very, very small. So LA is almost equal to 0. So putting this in this equation, LA becomes equal to 0, from which we can get IA is equal to VA minus kg into theta m dot divided by RA. Okay. So in this equation, I'm putting LA equal to 0, and I'm finding IA. So IA is equal to VA minus kg into theta m by RA. Okay. Now let us call this equation 8. Okay, this is my equation 8. Now putting in 7, we get, if you remember what was 7, equation 7 was this equation in terms of tau A, right? So this was my motor torque. So I know what is my motor torque, so I put this equation into motor torque, and what equation we get is putting in 7 we get Jm plus n squared JL theta m double dot plus Fm plus n squared FL into theta m dot is equal to KT is the motor constant. Okay, so tau is equal to KT into IA, and IA we have seen just IA was equal to VA minus kg into theta m dot divided by RA plus n times tau. Okay, so what we basically did, I just in the previous equation, so in this equation there was tau m, this is the motor torque. So motor torque we have seen is equal to KT into IA. So this I'm putting it there. Again I see IA is equal to VA minus kg into theta m divided by RA. Okay, so I put this all in this equation, and this is what I get. Now I can write it in short form as j into omega dot plus f into omega is equal to k into VA, okay, plus TD. I can write it in short. Okay, so this is a short way of writing it, in which case the terms JF is written this way. K is equal to KT into by RA. Okay, F is equal to, capital F is equal to FM plus N squared FL plus KT kg by RA. Okay, and J is equal to, these are called effective inertias, Jm plus N squared JL. I'm simplifying it, and TD is equal to N times TL. Okay, omega is equal to theta m dot. Okay. Now, what we observe from here is that if I look at the previous equation, this equation, so this is a first order equation. Okay, so this is a first order equation, and it can be that means the dynamics of a one link robot arm can be expressed as a linear first order differential equation. Okay, now the link rotates because of two inputs. Okay, one is VA and the other is TL. So the link rotates due to two inputs. What are the two inputs? One input is your the voltage that you're giving to the motor. There is one input. What is the other input? The other input is TD, the dynamic torque. Okay, so if you give an input of voltage, the motor will rotate, the link rotates. If I give a dynamic torque as a disturbance to the motor, to the link, it is also going to make it rotate. Okay, but it is interesting to note that the dynamics can be expressed as a first order differential equation. Now, because this equation now has two inputs, we find the transfer function using superposition. Okay, so this fellow has two inputs. So the way to go forward is to use superposition, where we assume once we'll say TD is equal to 0, then we'll say VA is equal to 0 and find the transfer functions. Okay, so using superposition, using superposition, first we assume that TD is equal to 0. If I say TD is equal to 0, then the transfer function omega s is equal to VA by S is equal to K by JS plus F. Okay, so if you go back to our previous equation here, in this equation, if I say TD is equal to 0, okay, then omega s is equal to K by JS plus F. Okay, so I've taken the Laplace transform also, so I've written it in Laplace domain. Okay, so using superposition and taking Laplace transform, okay, I get this transfer function. Now I put VA is equal to 0. If I put VA is equal to 0, then omega s by TDS is equal to 1 by JS plus F. Okay, so I get these two transfer functions. And if I draw the block diagram now, this is where the use of block diagram is, which we studied in the last class. So the first one is VAS as input of my block here is K by JS plus F, which is equal to omega s. Okay, and the second one is TDS. The second input is in the block diagram. It is going to come 1 by JS plus F, and the output is by omega s. Okay, now if I combining both of this, combining both the diagrams, what we get is VAS is equal to, there's a summing block plus plus, this is my 1 by Ks here, so 1 by K, which is coming in here, and the input here is TDS, and we get K by JS plus F here. Okay, and this is omega s. Okay, so what we have seen is I'm combining both the inputs. First I did superposition, got the transfer functions, then I combined them using superposition. Okay, and we can write this as omega s is equal to VA s plus TD s into 1 by k into k by Js plus f. Okay. Now the transfer function of the single link manipulator is given by, from here if I draw the if I draw the closed loop control system fully, okay, what it will look like is omega ds is equal to the summing block plus minus, here we have ds is the controller. Till now we have not put any controller. We have to control the robot link. We are only modeling the motion of the motor and the link without a controller. Now I have to put the controller. Okay, so this is 1 by k, and input here is TDS. This is k by Js plus f, and this is my omega s. And I put unity feedback, so it is 1 here, and I put it back here. Okay, this is my closed loop control system. Okay, now we have to put a controller here. This is my controller. So in the previous case there was no controller. Okay, here there is no controller. Now I'm putting a controller and I'm putting a feedback, unity feedback, and then I'm looking at a closed loop control system. Now what we do here is, first of all, we are, to simplify it, we are ignoring TD equal to 0, or ignoring the effect of TDS by putting, well, that's not right, I'm assuming TDS to be equal to 0. So I'm saying assuming TD equal to 0, then I have a single input, we have a single input system only. Okay, this is a reasonable assumption to make because n is very large. So it is going to cut that TDS and it simplifies our analysis. Now what we do is we observe the effect of putting, and now what we do is we design the controller, by putting different controllers by using first a P controller, then a PD controller, and then a PID controller, and then we observe the effects. Okay, so we are controlling designing a controller here now by using first P proportional, then proportional derivative, then proportional integral derivative. Where in the controller block is here, and then observe the effect in terms of response. Effects means response. Okay, so this is what we are doing to study our control system as we are proceeding. Now what we can do is, first we put a P controller. Okay, so the first thing that we'll do, let's call it case 1. So in case 1, control of the angular velocity of the link. This is a first order system, so we are controlling the angular velocity. Okay, this is the first thing that we are doing. Now so for controlling the first order system, and this is a first order system. Okay, we can go back and understand why this is a first order system, because if you look at this equation that we have written here, okay, the way we derived it here, so this is a first order system. Okay, so we are intentionally writing it this way so that we can analyze, first try to control the velocity, then we'll control the position. So here we are first trying to control the velocity of the first order system. So what we do is, so the first thing that we'll do is to, in case 1, we're going to put the controller ds is equal to k. Okay, kp is the position gain, and then see how the system behaves. So let us put ds equal to kp. Okay, so let us put ds equal to kp and see what is happening. So omega s is my summing block plus minus, and my controller now is kp. Okay, it's a proportional controller. This is going towards k into Js plus f, And remember that my TD, the dynamic torque is now 0. So there is no input here. Okay, there is no other input. And it is unity feedback, so I have 1 here. Okay, so this is my closed loop control system by using a proportional controller. Now the closed loop transfer function between omega s and omega ds, I need to find the transfer function. So transfer function between omega s and omega ds and omega ds. What is this equal to? This omega ds is the desired input is omega ds is given by omega s by omega ds, which is equal to kkp divided by j into 1 by s plus f plus kkp, okay, divided by j, bracket close, and just like this. So how do we find the transfer function of this particular case? So we find the transfer function by multiplying these two blocks, first this block into this block, okay, and then closing it. So what we do is we multiply kp. So how do we find the transfer function? So if I find the transfer function as we multiply kp into k, okay, so the first block is sorry, this is kp. So let me put it in bracket here, kp into k, and the bottom we have js plus f, okay, and yeah, okay, so this one is like this, and then we have unity feedback on this side, okay. So this is my reduction. So if I reduce it further, it becomes equal to, on top we have kp into k divided by js plus f on top in the numerator, and the denominator we have 1 plus gshs, so it is 1 plus gshs, which is kp into k divided by js plus f, okay. So then we further simplify this and we get it in this form, okay. So basically we are reducing to the form, we are taking kkp by j divided by j, and we are reducing it to a single s here, okay. So it is coming to the form 1 by s plus a in that form, okay, 1 by kkp divided by j into s plus a in this form, writing the denominator. So now we know what is the, now we want to examine the response of the system, okay. So if you're trying to examine the response of the system, that is basically control the angular velocity of the first order system, okay. So we are examining the step response. So let us examine the step response. So the step response for step input omega ds is equal to 1 by d. Okay, this is what we are examining now. Now the output is obtained by the inverse Laplace transform with omega ds equal to 1 by s, okay. So in my previous, what is my input? This one is equal to a step response 1 by s, okay. So we put theta ds here. So theta s is equal to theta ds into this transfer function that we got, okay. So theta ds here is equal to 1 by s, so it will go that side, okay. And so omega s is equal to this into this. So what we are going to get is the response of the system, okay, for a step input, and the responses of the form. So the response of for theta d equal to 1 by s, and taking Laplace transform and inverse Laplace transform. We get is of the form 1 minus exponential minus of f plus kkp by j into t. Okay, so it is of this one. Okay. So we have double brackets here. There should be a single bracket here. F k capital with j. This will be closed. Yeah. Okay. So this is the response of the system that we are getting. Okay. Now we have to note that as f, k, kp, j are all positive. Okay, this is these fellows are all positive. Okay, so we note that f, k, and kp and j are all positive. Theta omega t is bounded and approaches omega dt as time goes to zero, goes to infinity. Okay, so now we see in this expression that it is 1 minus exponential of this minus of f plus k kp by j into t. Okay, so because it is written this way, okay, because let me write it this way, yeah, because it is written this way, and f, k, kp and j are positive values. Okay, that means essentially that omega t, the time response of this, okay, is bounded and it approaches the input, which is omega dt, as time approaches infinity. So as time is going towards infinity, this system will tend to go towards the desired input. That's the first thing we observe. The second thing we observe is that the system is stable. The system is stable, and poles of the characteristic equation lie on the left of the imaginary axis, left of IM axis. In the last class we talked about the response and stability of the system, and we said that if the poles are on the left of your j omega axis, then your system is stable. Okay, so here we are seeing that the poles are towards the left of your j omega axis, and your pole is at, so where is the pole? Pole is at minus of f plus kkp, okay, divided by j. Okay, so a pole is showing it's minus, so it's on the left of your j omega axis. Now this is a proof that the system is stable and the system is going towards the desired input as time is going to infinity. So this is case 1. Now case 2 is in place of our okay, let us look at the response, step response. If you plot it, it becomes clearer. So step response of this, if I draw, this is my x-axis, this is a unit step input, and this is my time axis. So this is my step input here. And what will happen is this will go up like this, and it will become very slowly, it will come and go, and there as time is going to, this is omega d, okay, in terms of time. So what will happen is as time is going to infinity, this will slowly go and become equal to what is the desired value, okay, like that. Okay, as time is going towards infinity, it is going to reach the value of TDS. So this is the step response of this system. Now please note that we were controlling the angular velocity of the link. Now in the second case, let us control let us control case 2. Okay, let us control the angular position of the link. Now if I control the angular position of the link, we see that this is a second order system. Let us again, assumption TD equal to 0. In all cases we are saying TD equal to 0 to make it simpler. Okay, So in this case, we are saying that it is theta s by VAS is equal to K by S into JS plus F. Now it is S squared. You can see that at the denominator there is an S squared now. In the previous case, it was 1S. Now if I draw the control system, okay, so if I draw the control block diagram, so let me draw the block diagram. It is plus minus, and this is my theta ds. Then it is still a P controller, which is equal to K into S into JS plus F. So, okay. And this is theta S, and my feedback is unity feedback here. Okay. Now the closed loop transfer function, how do we find? Exactly the same way that we had done it in the previous case. We multiply Kp into K into K divided by S into JS plus F. So I multiply this into this. Then I close it by saying this is equal to the output by input is GS by 1 plus GSHS when I close the controls. Okay. So the closed loop transfer function is written like this. So the closed loop transfer function is written of the form theta s by theta ds is equal to K by Kp, okay, divided by S into JS plus F plus KKP, which is equal, which can be written, there is a just S squared at the bottom, okay, the denominator, which can be written in the standard form, which is omega n squared divided by S squared plus twice zeta omega n plus omega n squared. This is the standard way of writing a second order equation. The characteristic equation in the denominator has an S squared. Please note that. So in this case, omega n squared is equal to KKP divided by J, and F by J is equal to 2 omega zeta, zeta omega n, and zeta, which is the damping ratio, is equal to F by 2 root J KKP. Okay, these are standard terms which are used for the natural frequency and the damping ratio. So omega n is my natural frequency. So this is the natural frequency, and zeta is equal to damping ratio. Okay. So now we have put now for different values of zeta greater than 0, less than 1, it is underdamped. It is underdamped. Then zeta is equal to 1, it is critically damped. Zeta is critically damped. And then zeta is greater than 1, then it is overdamped. So these are the three conditions of zeta. Now for response, getting the response of our system, we can make the assumption that K, just to plot and see, Kj is equal to F is equal to 1, and for values of Kp, Kp values for zeta equal to 0.25, zeta is 0.25, then 1, 1.3, 4, 1/4, 0.147, in that way. Okay, and step input, we have a step input input of theta d equal to 1 by s. Okay, so what we have done is for the response we have put K is equal to J is equal to F is equal to 1, and Kp values of for zeta equal to 0.251, 1.3. So how did we find that? You can see the relation between for different values of Kp, we can find what is zeta from here. Okay, so for different values of Kp, we find what is zeta, and then we plot, and what we find is the response looks something like this, where we have this is my step input. Step input is 1 by s. Okay, so my step input is here. So what we get is for zeta equal to minus, okay, so zeta equal to is equal to 0.25. It is there. It behaves like this. For zeta equal to 1.3, it behaves for zeta equal to 1.3, it behaves like this. Okay, zeta equal to 1.3, it behaves like this. So we find that for different values of zeta, it behaves in a particular fashion. So it is underdamped, overdamped, or critically damped, which is how the response of the system also is. So this is my time axis. Okay. So when we are talking about design of this, what we are basically doing is we are making the assumption that kjf is equal to 1, and then putting different values of kp and finding the zeta, and then we are plotting. Okay, and the response looks like this for different values of zeta. Now for critically damped, we can find what we want. If our system is to be critically damped, then we know what is the corresponding value of zeta. Now let's look at the next part, which is case 3, which is PD control. PD controller. Okay, and my ds is equal to kp plus kv into s. In the previous case, the ds was equal to kp only, so it's a proportional controller. So the next, let's look at plus minus. Here my input is theta ds as usual, and it is kp plus kv into s. Okay, and my link is s into js plus k, and this becomes equal to theta s. Okay, and my input is 1 here. Okay, so this is my closed loop control system, and I have to find the closed loop transfer function of this. So the closed loop transfer function, how do we get it? We get this into this, then it is gs by 1 plus gshs. Okay, so what we do get is theta s divided by theta ds is equal to kkp plus s into kkv j into s squared plus s into f plus kkv plus kkp. Okay, so our the characteristic equation is in the denominator. This is what we get. Now the omega n and zeta are now determined by kp and kv. So omega n and zeta and omega n are determined by kp. There are two variables now, kp and kv. Okay, both of them. Now kp increases the system. If you increase, what is the effect of kp and kv? Let's look at that. Effect of kp and kv. Effect of kp and kv. See, if kp is increased, the system becomes faster. The system response becomes faster. So it rises much faster. If kv is increased, then the overshoot decreases. Okay, so this is the effect of kp and kv. Now for critical damping, we know that kv is equal to 2 root kp for critical damping. This condition holds. So what we can say here is that by putting different values, we can look at the response of the system, and once we look at the response of the system, if we are happy with it, so this is my response of the system, this is my t, okay, and this is step input. So if it is doing like this, or it is sluggish like this, or it is very nicely, it comes and stays, depending on that, this is my critical damping. So when it behaves like this, then we say that this is my desired system response. Okay, so this is essentially how we design a PD controller for this controlling the robot link. Now, P controller response we have seen PD controller response. Okay, now what about the PID controller response? Now, what we have seen in the last class is that the problem with a PD controller, the main issue is that there is a error steady state. Now the steady state error essentially means that as time is going to infinity, your output and input there'll be a small difference between them. It will never be exactly equal. Okay, why? Because of this equation. Let's look at it this way. So E double dot into Kp, or Kv into E dot plus Kp is equal to F disturbance. Okay. So in terms of this equation, which is basically a PD controller equation, in terms of error, now E is equal to theta d minus theta. So in our case, it is omega d minus omega. Okay. So this is the error. So in terms of the error dynamics, this is the equation for the error dynamics for a PD controller. Okay. And F disturbance is the force, the disturbance torque, which is always going to be there in a robot manipulator. So this fellow is never going to become equal to 0. So this will never be 0. Okay. So now if you look at this at steady state, E double dot is equal to E dot is equal to 0 because system is not moving. Okay. But if you look at the top equation, then Kp into E becomes equal to F disturbance. Okay. Divided by is equal to Kp into E is equal to F disturbance. So error becomes equal to F disturbance divided by Kp now. Now what is your F disturbance? It is N, the gear ratio, into the dynamic torque. Okay, Td. Okay, so Td was the dynamic torque, or okay, TL was the torque that side, into Kp. Okay, so when we started off by saying, we said that the torque that is going to come, okay, is tau L, which is the external disturbance torque that is coming. Okay, and your external disturbance torque is multiplied by the gear ratio before it comes onto the gear. Okay, so in our equation, when we wrote, if you go back to equation number 9, what we see is that, so our equation number 9, if we just go back a little bit to understand this, this is also very important to understand. So our equation 9 is this is our equation. So what we find is that there is a N into tau L. What is into TL? What is TL? TL is the disturbance torque, which is coming because of the dynamics. So this fellow is because of dynamics. Okay, and it is equal to N into the dynamic torque, TL. So when we are coming back here and looking at the error steady state, we find that the error steady state is equal to the product of the dynamic torque, which is my disturbance, into L, divided by Kp. Okay, so this means that error steady state is never going to become 0 for a PD controller. So very small error will be there, but the error is there. Now, so what you can do to reduce error, what we can do now, the first thing we can do is to increase Kp. Okay, so if I increase Kp, what will happen? You can see the error will decrease. And number 2, we can use a higher reduction. So using a higher reduction means X, N is less than equal to 0.01. Okay, much less than. How much smaller you can make it, that means you have a higher reduction, higher gear reduction. So this is the reason why in industries PD controllers are used for robot manipulators, because you can control the position very easily using a PD controller. There is some error steady state, but then it is a stable controller. So the main benefits of this PD controller is stable. We have seen that this is a stable controller because the root is on the negative side always. So whatever you do to Kp and Kv, it will always be stable. It will never become unstable. Okay, but there is an error steady state. So you can make the error steady state by looking at these conditions, but it's a stable controller. So industrial controllers are all PD controllers, most of them. Now, if you want to make the error steady state equal to 0, then we have to use a PID controller. So this is my, in the previous one, we had looked at case 3. Now this is case 4. Okay, so this is my case 4, where we are looking at a PID controller now. PID controller. Okay, now the PID controller, essentially ds is equal to, we add the integral term Kp plus Kv into S plus Ki divided by S. So that's my PID controller. Okay, so we are adding this integral term. Integral of what? Integral of the error. So as the time is increasing, it is integrating that error. That means your error is error is increasing. So the controller will try to make that equal to 0. Okay. So if I draw the closed loop control system of this is plus minus theta ds, and this is equal to Kp plus Kv into S plus Ki into S. On this side it goes K into S into Js plus F, and this is equal to 1. Okay. Now this is a PID controller. Now in a PID controller, what you can see here is that there is a 1 by S here, because this becomes 1 by S. So there is a 1 by S, Ki by S here, this one. So what will happen is, when we find the transfer function for this, you can multiply. How do you find the transfer function? We multiply this into this, then we do GS by 1 plus GSHS to get the total transfer function, theta ds, and this is my theta s. So if you do the output to input, theta s by theta ds, okay, what will happen is this will become a third order equation. We will see that the characteristic equation is equal to third order. Why is it third order? Because there is s squared here and there is another s there, so s into s squared will make it s cubed now. Okay, so s into s is squared and there is an s there, so it will make it a third order system. Now because you make it a third order system, stability is not guaranteed. Stability is not guaranteed. Okay. Now because stability is not guaranteed, if you put very high Ki, okay, if we end up putting a very high integral gain, then what will happen? The poles will become positive. That means it will and go to the right of the j omega axis. Poles becoming positive means it will go to right side of j omega axis or I omega axis, and that means it will become unstable. So although it appears that PID controller is better because in the sense that you can reduce the error steady state, okay, but what we see is that it has the other effect that if you're not very careful with the gains, then what will happen? It will become an unstable system. Now that is one. So the disadvantage of PID controller is, number one is PID controller, okay, is number one is that high Ki will make it unstable. Okay. Now number two is this integral e dt, Ki into integral dt, which is the I part. Okay, this is an integral, so it will tend to slow the system. It will make it slow, or it takes time. Okay. Now because it takes time, it will tend to make the system make it slower. Plus the cost goes up. Cost of controller goes up. Okay, because we are adding this integral now, and because of which the cost is going to go up. So some things we have seen in this lecture is that how do we control a robot joint using P control, PD control, and PID control. Now every joint has its own controller, okay, and the reason, the moral of the story for this lecture is that it works. The main moral of the story is a linear control system works reasonably well because of the fact that although there is dynamics, but the dynamic torque is reduced. The dynamic torque is substantially reduced by the gear ratio. So the gear ratio reduces the dynamic torque, because of which even if the link is moving and there is disturbance coming, but the gear ratio tends to cut it out. So the moral of the story is, if you want to control the position using a motor, you must have a gear ratio. If you try and control without having a gear ratio, you'll end up with severe problems for the controller. So wherever you look at position control applications, you'll always find that there is a gearbox sitting there. Now the function of the gear is essentially to cut that external disturbance which is coming, because fundamentally a robotic system is a nonlinear control system. Now here again we made an assumption. The assumption is that we had our parameters like J, then we have parameters like friction F, and then we had spring like K. But in an MBK system, what we have been talking about so far, is that we are making the assumption that M, B, K are constants. Now you know in reality that your friction is not linear, okay, and similarly your spring constant K is again not linear. The behavior, I mean, so K is not a constant. Similarly, B is not a constant. They can vary. Okay. So next class, what we'll be looking at is how to deal with nonlinearities in the system. And nonlinearities, for example, in the friction model, or nonlinearities in the spring. A real spring is nonlinear, you know that. So if you stretch the spring, it will stretch linearly for some time, then it will become nonlinear. Similarly, if you compress the spring, it will compress linearly for a short portion, and then it will become nonlinear. You can't squeeze anymore. So in the next class, we'll be looking at how to deal with the nonlinearities in the control model that we have made, and we'll look at how to deal with variable friction and nonlinear springs. So we'll stop today. Thank you.